sometimes, in order to solve integrals, you don't need brute force calculations or tedious equations. Rather, you need insight. And in this video, we'll go over 3 integrals that demonstrate that. So, for example, take a look at this one. I want you to compute the value of this integral. And it might seem kind of complicated, but the right solution, or the most efficient solution, will take, probably just a few lines, maybe 2 to 3 lines. So try to see if you can spot that. Are you done? Okay, so yeah, it looks kind of annoying because of this natural log, but I hope you noticed that there is actually some symmetry we can exploit here. Consider this. If you were to let x equal to pi over 2 minus y, well, this integral would become the integral of, we'll worry about the bounds later. So it's the integral of the natural log of 1 plus sine of pi over 2 minus y, and then over 1 plus cosine of pi over 2 minus y, and then d pi over 2 minus y. And as for the bounds, which we'll now worry about, notice that in the original integral, we had x going from 0 to pi over 2. And now, well, we made the substitution, so now pi over 2 minus y will go from 0 to pi over 2. And therefore, this is equivalent to having y go from pi over 2 to 0. So the bounds are the lower bound to be pi over 2 and the upper bound to be 0. Okay, now let's simplify this. This is equal to the negative integral of 0 to pi over 2 of, and notice that over here, sine of pi over 2 minus y, that's cosine of y. And likewise down here, we have a sine of y. So this is equal to natural log of 1 plus cosine of y over 1 plus sine of y. And of course, over here, this is equal to negative y, dy. Sorry, not negative y, just negative 1, right? So negative 1. Okay, and notice that, this is the key insight, notice that this over here is exactly the reciprocal of this. So what does that mean? Well, we can write the natural log as the following. This is equal to the negative integral of 0 to pi over 2 of the negative of the natural log of 1 plus sine of y over 1 plus cosine of y. Right, and then this negative 1 can combine with this negative to become positive, so this just goes away. Okay, now, do you see what we have done here? Well, take a look at this. If we were to let this original integral to be equal to I, and this is equal to this, equal to this, equal to this, well, notice that this over here is literally just equal to negative I. So therefore, we have deduced that I is equal to negative I, so therefore 2I is equal to 0, I is equal to 0. And therefore, we have computed the value of our integral. The key insight was to focus on the symmetry of the fractions, which produced a very nice equation, right, for us to work with. Okay, so now for our second example. And yes, my handwriting is slightly bigger than the previous one. However, this integral is also very elegant. So if you didn't get the previous one on your own, then why don't you pause the video and try to figure out this one. Done? Okay, so I know that we have a natural log over x, and that doesn't seem like something that we can integrate very easily. However, there is something that should tug out at our intuition. And in particular, we see that natural log of 1 minus x is up there. And there's a very nice power series for natural log of 1 minus x. So let's try substituting that in. So this is equal to the integral from 0 to 1 of, we can replace natural log of 1 minus x with its power series, that is negative sum as n goes from 1 up to infinity of x to the n over n. And then at the bottom, we still have an x over here. Okay, and now we can clean this up a little bit. We have x at the bottom, so we can subtract the exponent by 1. So this is equal to the negative integral from 0 to 1 of the sum as n goes from 1 up to infinity of x to the n minus 1 over n dx. Now, consider this. the summation of this expression converges, right? It's not going to be infinite. And the integral from 0 to 1 of this expression is obviously not going to be, well, we can see that it's not going to be infinite. It's going to be some finite value. So we can actually exchange the order of the integration sign and the summation sign. So we can write this as the negative summation as n goes from 1 up to infinity of the integral of 0 to 1 and then of x to the n minus 1 over n dx. Now, check this out. This integral is anything but hard to integrate because we just use reverse power rule, right? Using reverse power rule, this integral, well, let's first write the summation, right? We still have a summation on the outside, but this integral using reverse power rule just becomes 1 over n squared. And if you know the famous Basel problem, you know what this sum is going to be equal to. In particular, this is well known to be equal to pi squared over 6. So this over here is the value of this integral. Very cool, right? It's kind of cool how the power series comes in clutch. Okay, so for our third example, we have this integral, and we have a and b to be fixed numbers. In particular, they are positive real numbers. So how can you compute this integral? So I know this one looks a bit weird because, I don't know, it just looks weird, right? And I will admit, I think it is harder than the previous two that we've just done. However, there is a very elegant way to tackle this problem. Just consider this integrand. It looks like something that you would get from computing a definite integral. And indeed, check this out. If you were to integrate from from a to b of e to the negative cx dc, so not dx, dc, if you were to integrate this expression, well, this would actually equal to this. It would equal to the integrand. In particular, I'll just write it out over here, right? Now, of course, this isn't actually very hard to verify for yourself. And I'll do a quick verification here if you want. So to compute this, you just let u equal to negative cx, and then now you have c equal to u over negative x. And then now, this integral, well then this would just become the integral from, this would actually become negative c, not negative, xa, right? And then up to negative xb of e to the u times 1 over negative x du. So this is the integral that you get from doing this substitution. And of course, you can move this 1 over negative x out because, again, this is du, all right, not dx. And then you have e to the u du. Surely that's not a problem. This will just equal to this if you were to work it out. So therefore, we can actually replace this integrand with this integral expression. Okay, so now we've made our substitution. And I know it looks pretty horrible. It looks pretty messy. We have double integrals. However, there's actually a very nice, insightful move we can perform next. Remember in the second problem, in our previous problem, we were able to swap the order of the summation and the integral, and that in turn created a nice expression within the inside. In particular, it was a very easy integral within the inside to calculate, right? And in this case, we can do something very similar. We can swap the order of the integration signs, and that in turn will create something within the inside that will be much easier to calculate. Check this out. So this is equal to the integral from a to b of the integral from 0 to infinity of e to the negative cx. Of course, you have to swap these, so dx dc. Now, if you want to rigorously prove that you could swap the integration signs, I'll leave that to you. It's pretty intuitive, but if you want a formal proof, you can do it if you want. So now, consider this. This integral over here, that's not a hard integral to evaluate. In fact, okay, this is a standard integral that you get from, I don't know, it's not too fancy, right? You can calculate this very easily. This is just going to be equal to the integral from a to b of 1 over c. Right? And now, this is not hard, right? This is just equal to the natural log of b minus the natural log of c, because the natural log of 1 over c, the integral of 1 over c, that's natural log of c. And, okay, this should not be c, this should be a. And therefore, our answer, written more compactly, will be equal to natural log of b over a. As you can see, one substitution, one clever move, the answer just falls out. Anyways, that's going to be it for this video. I hope you enjoyed it. I hope you found it interesting. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.